Good morning all. In today's session we are going to handle the topic on equivalent values of drive parameters and their numerical problems. In actual practice, different parts of the loads are connected through different mechanisms. In some cases they will be connected through V-belts, and in other cases they will be connected through gear trains and crankshafts, etc. Different parts of the loads will have different speeds, and in some cases they will be having different types of motion such as rotational as well as translational one. In this video session, our main aim is to determine the equivalent moment of inertia and the equivalent torque value, both referred to the motor shaft, which is considered as the reference one. First, we will consider the case in which loads are having only rotational motion. For that, the system which is taken into consideration are shown here. Here there is a motor and a load which is actually directly coupled with the motor, and another load which is coupled through a gear system. You have studied in your basic mechanical engineering course. For a gear, the gear ratio or the tooth ratio can be written as A is equal to omega m1 divided by omega m, which is same as n by n1. That is actually the gear tooth ratio. For this system, J0 indicates the equivalent moment of inertia for this motor load system. That is, this load is actually directly coupled with this motor. So for this complete motor load system, their equivalent moment of inertia is indicated as J0. J1 is actually indicating the moment of inertia of the load which is coupled to the motor through a geared system. Let's assume the equivalent moment of inertia for this complete motor load system as. In order to determine the equivalent moment of inertia for this complete motor load system, we will assume this transmission system as a lossless one. That is, the losses which are occurring in this transmission system are not taken into consideration. Or else we can say that the system is said to be a 100% efficient one. That is the assumption which we are taken into consideration while obtaining the standard relation for equivalent moment of inertia. Then we can say that the kinetic energy of the equivalent moment of inertia for this complete motor load system is same as that of the sum of the kinetic energy of all the moving parts present in this motor load system. Kinetic energy of the equivalent moment of inertia for this complete motor load system can be said to be half j omega m square, where j is the equivalent moment of inertia for this complete motor load system and omega m is actually the reference speed. As I have mentioned before, the motor shaft is taken as the reference one. So now this half j omega m square term has to be equated with the sum of the kinetic energy of all the moving parts in this motor load system. As these two are coupled together, their kinetic energy can be written as half j0 omega m square, and the kinetic energy of this load can be written as half j1 omega m square. So the sum of the kinetic energy of all the moving parts in this motor load system can be written as half j0 omega m square plus half j1 omega m square, half j1 omega m1 square. This has to be equated with half j omega m square. That relation is shown here. Further simplifying it by cancelling the half in both RHS and LHS and thereafter dividing the whole relation with omega m square, we will be able to simplify this relation into this particular form. As I have mentioned in the previous slide, the ratio omega m1 divided by omega m is actually a1. Hence this j can be written as j0 plus a1 square j1. Suppose if the system had Suppose if there were m other loads having different moment of inertias connected through different gear trains of different gear ratios, then the standard relation for equivalent moment of inertia gets modified into this form. All of you must remember this relation, then only you will be able to solve the problems associated with this. That is, j is equal to j0 plus a1 square j1 plus a2 square j2 up till am square jm, where j0 is actually the moment of inertia of the direct motor load coupled system, and j1, j2 up till jm are the moment of inertia of different loads, and a1, a2 up till am are the gear ratios of the different gear trains. So all of you must remember this relation. Next we have to find out the relation for equivalent torque. In order to find out the relation for equivalent torque, the losses in this transmission system are taken into consideration, although they were not taken into consideration while obtaining the relation for equivalent moment of inertia. Equivalent torque for this complete motor load system is taken as TL. So the power which is being supplied in this complete motor load system by the motor is taken as TL into omega m, As you know, the standard relation for power is T into omega. In this case, we have taken the speed as omega m because this motor shaft is taken as the reference. So we can say that the power which is being delivered by the motor to this complete load system is TL into omega m, where TL is actually the equivalent torque referred to this motor shaft. To obtain the standard relation for equivalent torque, we will equate the power delivered at the motor and the power which is being received at the load sides. As I have mentioned now, the power delivered by the motor is TL into omega m, and the power which is being received by this load is TL0 into omega m, as this load is also rotating at the same speed as that of the motor, as both are directly coupled. The power output of this particular load is TL1 into omega m1, but we are taking into consideration the power which is being received at the load side, or the power which is being fed to the, or the power input at this load side. TL1 into omega m1 will be giving the power output of this load. So the power input can be obtained by dividing this power output with the gear efficiency. The gear efficiency here is considered as nu 1. So we can obtain the relation for power received at this load as TL1 into omega m1 divided by efficiency, that is nu 1. So by equating the power delivered by the motor and the power which is received at the load sides, we will get the relation as TL into omega m is equal to TL0 into omega m plus TL1 into omega m1 divided by nu 1. This is actually the transmission efficiency of the gear system. Further dividing this whole relation by omega m, we can simplify this into standard form as TL is equal to TL0 plus A1 TL1 divided by nu 1. Just like we mentioned in the case of equivalent moment of inertia, considering the fact of numerous loads of having different moment of inertia connected through different gear trains of different gear ratios, the same way we can write the standard relation for equivalent torque also. Consider the system is having m other loads which were connected through different gear trains having different gear ratios. Then the standard relation for equivalent torque can be written as TL is equal to TL0 plus A1 TL1 divided by nu 1 plus A2 TL2 divided by nu 2 up till AM TLM divided by nu m. So these two are the standard relation for equivalent moment of inertia and equivalent torque. All of you must remember these relations. These relations are very important. You don't need to by heart them. If you know how to write these relations, you can easily obtain the standard relation. So just be thorough with this concept. All of you must keep in your mind that while obtaining the relation for equivalent moment of inertia, we have assumed the system as a lossless one. That is, we haven't taken into consideration the loss of the transmission system. Whereas while obtaining the relation for equivalent torque, we are taking into consideration the losses in the transmission system. That's why this efficiency term is occurring here. Otherwise, the system would have been 100% efficient and the value of this nu 1 would have been 1. So far we have considered that the different parts of the loads were connected through gear trains, but it's not necessary that always the systems must be connected through gear trains. There are other mechanisms also, such as belt drives, crankshafts, etc. Suppose if different parts of the loads were connected through a belt drive, then also the same relations will be valid, but this A1, A2 will not be indicating their teeth ratio because there are no teeth in the case of belt drive. Instead, they will be indicating the ratio of diameters of the wheels driven by the motor to the diameters of the wheels mounted on the loft shaft. Usually problems related with the gear trains are only asked, so you don't need to know much in detail about the belt drive system. So far we have considered the loads with the rotational motion alone. Now we are going to consider the system having translation motion also. If you observe in this system, there are two loads. One load is directly coupled with the motor and the other one is actually a translational system which is coupled with the motor through a transmission system. Since this load is actually a translational one, they will be having linear velocity or they will be having linear motion. This is actually a rotational to linear transmission system. So in this scenario there are two loads, one is having rotational motion and the other one is having linear motion. M1 is actually the mass of the load coupled through a transmission system, and F1 is the force of load coupled through this transmission system. V1 is the linear velocity of the load coupled through this transmission system. This will be very much like a hoist operation. Just like the previous case, for this system also, for this motor load system also, we have to identify the relation for equivalent moment of inertia and the equivalent torque. So the equivalent moment of inertia for this complete system is assumed as J. As in the previous case, the losses in the transmission system are neglected here also. So while equating the kinetic energy of the equivalent moment of inertia and the kinetic energy of the various moving parts, that is sum of the kinetic energy of the various moving parts, we will be able to obtain the standard relation for equivalent moment of inertia. Kinetic energy for this motor load system will be half J0 omega m square, and kinetic energy for this mass system or this translational system is half m1 v1 square. Kinetic energy of the equivalent moment of inertia for this complete motor load system is half j omega m square, where omega m is taken as the reference speed, that is actually the speed of the reference motor shaft. So while equating this relation, we will be able to obtain the standard relation for equivalent moment of inertia as j is equal to j0 plus m1 into v1 by omega m the whole square, because in this relation, for simplifying it, we will be cancelling this half terms, and thereafter we will be dividing this whole relation with omega m square. Then we will be obtaining the standard relation for equivalent moment of inertia as j is equal to j0 plus m1 v1 divided by omega m the whole square. Similarly, with the case of the rotational system, here also we will be considering m other loads with translational motion having different velocities of v1, v2 and vm, and different masses of m1, m2 up till m, just like we have seen in the case of loads with the rotational motion. In this case also we will consider there are m other loads with the translational motion with velocities v1 up till vm and masses m1 up till mm. Then the standard relation for equivalent moment of inertia can be written as j is equal to j0 plus m1 into v1 by omega m the whole square plus m2 into v2 by omega m the whole square up till mm into vm by omega m the whole square. Next, we have to find out the relation for equivalent torque. For that, we will take into consideration the losses of this transmission system. Then the power delivered by the motor is same as that of the power which is being received at the load side. The power which is being delivered by the motor can be written as TL into omega m, where TL is indicating the equivalent torque, and the power which is being received at the loads as TL0 into omega m and F1 V1 divided by nu 1. The power output of this mechanical translational system is usually written as F1 into V1, that is force into velocity. Just like how we are writing the relation for power in a rotational system, that is actually torque into omega. Similarly, we can write the relation for power in translational system also, that is force into velocity. But this force into velocity will be giving the output power for this mechanical translational system, but for the relation we need to find the power which is being fed to this mechanical translational system. That can be easily identified from the output power by dividing it with the transmission efficiency. That's what we are doing it here. In this term, we will be dividing the output power F1 V1 divided by the transmission efficiency. So after equating the power which is being supplied by the motor with the sum of the power which is being received at the load side, we will be able to find the standard relation for load torque as, we will be able to find the standard relation for equivalent torque as TL is equal to TL0 plus F1 by nu 1 into V1 by omega m. Just like we have considered in the case of equivalent moment of inertia, for equivalent torque also, if there are m other loads having different velocities from V1 to Vm with their mass varying from m1 up till mm, then the standard relation for equivalent torque can be written as TL is equal to TL0 plus F1 by nu 1 into V1 by omega m up till Fm by nu m into Vm by omega m. So all of you must remember these two standard relations also. If you find it as difficult to by heart these relations, then if it's difficult for you to remember these relations, then you must remember these steps from which you can deduce the standard relations. Next, we are going to see some numerical problems. This is the first problem. A drive has the following parameters. T is equal to 150 minus 0.1 n Newton meter, where n is actually the speed in RPM, and the load torque is given as 100 Newton meter. This is the relation for motor torque. Initially, the drive is operating in steady state. The steady state condition is achieved when the value of motor torque is same as that of the load torque. In our last class, we have obtained the relation for motor torque as T is equal to TL plus J into d omega m by dt. In that relation, J into d omega m by dt were the dynamic torque component which used to occur only during the transient condition. So in this case, it's very clearly given that the drive is operating in steady state. So we don't have to take that dynamic term into consideration. So while neglecting the dynamic term, the relation becomes T is equal to TL under equilibrium condition. The characteristics of load torque are changed to TL is equal to minus 100 Newton meter. Initially the load torque was TL is equal to 100 Newton meter. Thereafter it is being changed to minus 100 Newton meter. You are asked to find the initial and final equilibrium speeds. The equilibrium speeds can be found out by equating the value of motor torque with the load torque. So in case 1, we will be equating the motor torque with the load torque, that is 150 minus 0.1 N with 100 Newton meter. That is done here. Thereafter, further solving it, we will be able to obtain the equilibrium speed as 500 rpm. In case 2, the load torque is changed to minus 100 Newton meter. So we have to equate the relation for motor characteristics with that of the load torque. That is 150 minus 0.1. This is actually not Newton, this is actually the speed term. So 150 minus 0.1 N is equal to minus 100. Further simplifying this, we will be able to obtain the equilibrium speed as 2500 rpm. This is a simple problem. Now let's see the second question. A motor is used to drive a hoist. Motor characteristics are given by quadrants 1, 2 and 4. T is equal to 200 minus 0.2 N Newton meter. Quadrants 2, 3 and 4. T is equal to minus 200 minus 0.2 N Newton meter. Just like in the previous problem, this N is indicating the speed in rpm. When hoist is loaded, the net load torque is 100 Newton meter. When it is unloaded, the net load torque is minus 80 Newton meter. You are asked to find the equilibrium speeds of operation in all the 4 quadrants. This is a very important question. This has been asked once in the previous year university question paper. So when such sort of problems are asked, you need to first draw a rough diagram of the data given in the problem. So you have to draw the 4 quadrants, first, second, third and fourth. Torque is taken along x-axis and speed is taken along the y-axis, speed in rpm. Now the characteristics of motor are given for different quadrants of operation. For the first, second and fourth quadrant of operation, the motor characteristics is given as 200 minus 0.2 N. So you just need to draw a line through the first, second and the fourth quadrant. Through the first, second and fourth quadrant, I have drawn a line here, and this is indicating the characteristics. T is equal to 200 minus 0.2 N. For the second motor characteristic, that is lying along quadrants 2, 3 and 4, that is T is equal to minus 200 minus 0.2 N. You have to draw another line through quadrants 2, 3 and 4, and this line will be indicating the characteristics minus 200 minus 0.2 N. You can easily find out the intersection points. In order to find out the values at this intersection, you have to equate the value of speed as 0 in the torque characteristics. Then you will be able to find the torque value as 200, because at this particular point the value of speed is 0. So while equating speed is equal to 0 in this characteristics, you will be able to find the value of torque at this intersection point. Similarly, at this particular point the value of torque is 0. So in order to obtain the value of speed, you have to equate the value of torque in this characteristics relation as 0. So while equating T is equal to 0, you will be able to obtain the value of speed as 1000 rpm. Similarly, with the second characteristics also, you can obtain the intersection points. One is at minus 200 0 and the other is 0, minus 1000. Now let's consider the situation of loaded case. So under loaded condition, the motor is loaded with a load torque of 100 Newton meter. As this point is indicating 200 Newton meter means definitely the load torque will be coming somewhere around here, exactly the midpoint between this origin and this point. So you have to find out the speed corresponding to this point. Just like in the previous problem, the equilibrium speed can be determined by equating the motor characteristics with the load torque. So in this case also, for finding the equilibrium speed corresponds to the load torque of 100 Newton meter in the first quadrant, we will be equating 200 minus 0.2n with the 100. Then further simplifying, we will be able to obtain the speed as 500 rpm. This is actually the equilibrium speed in quadrant 1. When motor is in the second mode of operation, that is when motor is possessing this characteristics, and if the load torque is 100 Newton meter, then the operating point will be somewhere over here. See, somewhere over here it will be. In this, if the motor is following this particular characteristics, then definitely the operating point will be somewhere over here. So that will be the fourth quadrant of operation under loaded condition. So you can obtain the equilibrium speed corresponding to this point by equating the value of minus 200 minus 0.2n with the load torque, that is actually 100 Newton meter. That is also done here, and we have obtained the speed as minus 1500 rpm. That is the equilibrium speed in fourth quadrant of operation. Next case is the motor is in unloaded condition. When the motor is in unloaded condition, still there will be some amount of load torque, that is a minus 80 Newton meter. From this intersecting point, it's very clear that minus 80 will be lying somewhere between this origin and this intersection point, because this point corresponds to minus 200 Newton meter. It will be somewhere, it will be coming somewhere over here. So corresponding to that minus 80 Newton meter, you have to obtain the operating point in first characteristic as well as in second characteristic. In order to obtain the operating point in first characteristic, what you have to do is you have to equate the relation corresponding to this characteristic with the load torque of minus 80 Newton meter. That is done here. 200 minus 0.2n is equal to minus 80, and we have obtained the speed as 1400 rpm. That is, at this operating point the speed will be 1400 rpm. Similarly, if the motor is possessing this characteristics and if the load torque is minus 80 Newton meter, then their equilibrium speed will be at this point somewhere over here. So that can be determined by equating this minus 200 minus 0.2n with the minus 80 Newton meter. That is also done here, and the value of n is found out to be minus 600 rpm. That is, during loaded operation we have determined the speed in first quadrant and fourth quadrant, and during unloaded operation we have determined the speed in second quadrant and third quadrant. Hope it's clear for you. This problem is very important. I will just brief it once again. In this problem, you are asked to find the equilibrium speed in all these four quadrants of operation. The motor is possessing two characteristics, and the characteristics relation are given. And the first characteristics is lying in first, second and fourth quadrant. So I have drawn a line touching all the three quadrants, that is first, second and fourth quadrant. Similarly, the second characteristics is lying in second, third and fourth quadrant. So I have drawn another line which is passing through the second, third and fourth quadrant. From both these characteristics we can easily obtain their intersecting points. Once after the intersection points are determined, we can find the corresponding load torque positions. Under loaded condition, the load torque is given as 100 Newton meter. So definitely this particular load torque will be lying between, exactly lying at the midpoint between the 0 and 200 Newton meter. So we will be able to find the operating point in characteristic 1 somewhere over here, and correspondingly we will be able to find the operating point in characteristic 2 somewhere over here. Then equating the relation for motor torque with that of the load torque in these 2 points, we will be able to identify their equilibrium speed in quadrant 1 and 4. Similarly with the case during unloaded operation, in the case of unloaded operation, it is very clearly given that the load torque is minus 80 Newton meter. So it's clear that it will be lying somewhere between this origin and minus 200 Newton meter point. Corresponding to that point of load torque, we will be able to find the operating points in characteristic 1 and characteristic 2. Then in order to find the equilibrium speed, just like in the previous case, we will be equating this characteristic with the minus 80 Newton meter. Both these characteristics with minus 80 Newton meter and the equilibrium speed in quadrant 2 and quadrant 3 can be easily found out. Now let's see the next problem. A motor drives 4 loads two have rotational motion and two translational motion. Moment of inertia of the motor is 1.2 kilogram meter square. Please make the correction, here it's meter square. Motor runs at a speed of 1000 rpm. Following are the details about the four loads. The details are given in this tabular column. You are asked to determine the equivalent inertia of system and the power rating of the motor. In this problem, all of you must be very careful about this motor speed. Here the motor speed is given in rpm, not in radians per second. So in order to determine the value of the equivalent moment of inertia and the equivalent torque, we need to find the value of omega m, that is actually the speed in radians per second, not in rpm. So we have to convert this rpm into radians per second first. That is done here. Omega m is equal to 2 pi n by 60 and the speed in radians per second is 104.71 radians per second. First we will find the equivalent inertia. So the standard relation, you have to write the standard relation first. So while writing the standard relation, it's very clear that there are two rotational loads and two translational loads. So a1 square j1 and a2 square j2 indicates the rotational loads, and m1 v1 by omega m the whole square plus m2 v2 by omega m the whole square indicates the translational loads. J0 represents the moment of inertia of the motor. The values of J0, J1, J2, M1, V1, M2, V2 all are given directly in the problem. We have determined the value of omega m from the speed which is given in RPM. The values of A1, A2 are not given directly. You can determine it by using the relation of gear ratio. That is A1 is equal to N by N1 is equal to omega M1 divided by omega m. Here we will be using A1 is equal to omega m1 divided by omega m. Either you can convert this into radians per second and do the division, but it's not necessary because the motor speed is also given in RPM here. So instead of omega m1 we can write it as n1 divided by n, that is 200 divided by 1000 RPM. That n1 and n1 is not the teeth ratio, please keep in mind. Here I represent n1 as the capital N1 as the speed of the driven system and capital N as the speed of the driver. Therefore A1 is equal to 200 by 1000, that is 0.2. Similarly A2 is equal to 200 by 1000, that is also 0.2, because both these are rotating at the same speed of 200 rpm. So now we have identified all the terms in this relation. So after making suitable substitution we can easily find out the value of J, and in this case it is found out as 1.953 kilogram meter square. Next you are asked to determine the power rating of the motor. As we have seen in the previous slides also, the power can be identified by using the relation torque into omega. So in this case it will be TL into omega m, where TL is actually the equivalent torque and omega m is the speed in RPM of the motor shaft. Omega m is already identified here. Next we have to find out the value of TL. For that we will be using the standard relation A1 TL1 by nu1 plus A2 TL2 by nu2 plus F1 by nu1 dash into V1 by omega m plus F2 by nu2 dash into V2 by omega m. So if we are seeing in the standard relation, there are different efficiency term. This nu1 and nu2 is indicating the efficiency of the gear trains, and nu1 dash and nu2 dash represents the efficiencies of the transmission system, that is a rotational to translational transmission system. But in the problem, in the question, it's very clearly given that all these losses are neglected. So since there are no losses, as this is a lossless system, definitely the efficiency will be 100%. So for all these values we can make the substitution as 1. The corresponding values of TL, TL2, F1 and F2 are given here. A1, A2 value we have already determined. nu1, nu2, nu1 dash, nu2 dash value is taken as 1, as this is a lossless system. Omega m value is also identified here. So after making suitable substitutions, we can determine the value of TL also, that is 7.975 Newton meter. But in the problem, you are asked to find the power rating of the motor. To determine the power rating, we have to multiply this load torque with the speed of the motor shaft in radians per second. The speed of the motor shaft in radians per second is 104.71. You have to multiply this with the equivalent torque. Then we will be able to obtain the total power which is being developed by the motor. This is also a very important problem. Similar problems were asked for the previous year university question papers also. Let's see the fourth problem. A weight of 500 kg is being lifted up at a uniform speed of 1.5 meter per second by a winch driven by a motor running at a speed of 1000 rpm. Moment of inertia of the motor and winch are given, that is 0.5 kg per meter square and 0.3 kg per meter square. You are asked to find the motor torque, that is the equivalent torque, and the equivalent moment of inertia referred to motor shaft. In the absence of weight, motor develops a torque of 100 Newton meter when running at 1000 rpm. That is, in the absence of this weight means the torque developed will be TL0. So the TL0 is actually the torque of motor alone, as there are no load which is coupled directly with this motor. So the value of TL0 is given as 100 Newton meter and the value of speed is given in RPM here as 1000 RPM. So from this you can easily determine the value of omega m by multiplying it with 2 pi by 60. See, whenever such problems are asked, it's better to draw a simple diagram so that it will be easy for you to write down the standard relations. See, in this diagram, the motor is represented here and the winch is shown here. This is actually the weight system which is having translational motion with a linear velocity of 1.5 meter per second. In order to find the equivalent moment of inertia, we will be using the standard relation J is equal to J0 plus JW. Here actually this winch is having rotational motion. As far as this motor is concerned, this winch is actually a rotational load and this is translational load. So we can write the relation as J is equal to J0 plus moment of inertia of the winch, which is actually having rotational motion. As this is having translational motion, the relation becomes m into v by omega m the whole square. Make suitable substitutions, we can identify the value of equivalent moment of inertia. Similarly, with the case of equivalent torque also, T is equal to TL0 plus F by nu into V by omega m. Make suitable substitution for TL0 as 100 Newton meter and omega m as 2 pi into 1000 by 60. The value of F is not given directly in the problem. Instead, it is given that it is used to raise a weight of 500 kg. So definitely the force which is experienced by this mass will be m into g. So the value of F in this relation is 500 into 9.8. As there is no mention about the transmission efficiency, by default we can assume it as a lossless system. So for this efficiency term we can make the substitution as 1, because for a lossless system the efficiency will be 100%. Thereafter making the suitable. All these 4 problems discussed here are exercise problems provided in the Fundamentals of Electrical Drives textbook by Gopal K. Dubey. The solution for these problems were not given in the textbook. Now a solved example from that textbook is given here as an exercise for you. All of you must try this problem by yourself, find the answer and share it in our WhatsApp group.